The California Institute of Technology presents Project Mathematics, a series of modules, each consisting of a computer-animated videotape together with a workbook. Each module emphasizes visual aspects of topics in high school mathematics by using motion, color, and sound as an extension of the chalkboard. Live action relates mathematics to real life. Images from original documents help place topics in historical and cultural perspective. The program is divided into bite-sized segments, labeled with slates, like this one. These slates tie the video to the corresponding section in the workbook and encourage interaction between students and teachers.
We encourage you to look at the material more than once. Some of the material goes by quickly, but you can use the remote control to pause or back up and review a scene. For information about the project, write to Project Mathematics, 1-70 Caltech, Pasadena, California 91125, or see our website, www.projectmathematics.com.
The program begins with a brief review of prerequisites. This program uses rectangular coordinates with a horizontal x-axis and a vertical y-axis to display graphs of polynomials. For example, on the graph of this polynomial, the vertical y-coordinate of each point is equal to the square of the horizontal x-coordinate. Here are more examples. Constant polynomials, their graphs are horizontal straight lines. Linear polynomials, that is of degree 1, their graphs are also straight lines. The graphs of quadratic polynomials of degree 2 are called parabolas. Cubic polynomials of degree 3, these graphs are called cubic curves. And here are some graphs of polynomials of higher degree you may or may not have seen before. In this program, we'll become better acquainted with some of these curves. This one of degree 7 looks like a roller coaster. When a basketball player makes a beautiful shot like this, the ball's path is very nearly a parabola. Parabolas were studied by the Greek geometer Apollonius in the 3rd century BC. Much later, in the 17th century, Galileo showed that parabolas play an important role in physics. If you neglect air resistance, any projectile moves along a parabola if it is propelled forward and upward and allowed to fall under the influence of gravity. To make a sailboat glide smoothly through the water, naval architects use cubic curves to shape the hull. Sometimes pieces of several cubic curves are fitted together to form new curves called splines. This image of a television test signal is not the graph of a polynomial because it oscillates up and down forever. But part of it can be closely approximated by graphs of polynomials. Here are some approximations: linear, cubic, and higher degree. See how the polynomials fit the curve better and better as the degree increases. Two French scholars, Pierre Fermat and René Descartes, made a landmark contribution to mathematics in the 17th century when they introduced coordinate systems and described geometric figures with numbers and algebraic equations. For example, this line is described by the algebraic equation y equals x. If you take any point on the line, say this one, its vertical y coordinate is equal to its horizontal x coordinate. If you move the line up by 1 unit, the new equation is y equals x plus 1. You can also move the line up by any amount, or down by any amount. This line is described by the equation y equals 1/2 x. For each unit you move forward along this line, your elevation increases 1/2 unit. Change in vertical distance divided by change in horizontal distance is called the slope of the line. Parallel lines have the same slope. The equation y equals 2x describes a line with slope 2. The bigger the slope, the steeper the line. Horizontal lines have slope 0, and when the slope is negative, it's all downhill. The slope is the number multiplying x. Again, we can move a line up or down without changing the slope. Analytic geometry describes geometric figures by algebraic equations called Cartesian equations in honor of René Descartes. For example, a line of slope m has Cartesian equation y equals mx plus b. The Cartesian equation for this parabola is a storehouse of information about the curve. For any point on the curve, the vertical coordinate y is equal to the square of the horizontal coordinate x. The curve passes through the origin and is symmetric about the y-axis. The equation does not change when x is replaced by negative x. Let's see what happens to the equation when we shift the graph up or down. If we move the graph up 1 unit of distance, the new graph has the equation y equals x squared plus 1. If we move it vertically by any amount, the equation is changed by adding or subtracting that amount. All these examples illustrate vertical translation. Now let's see what happens if we translate the curve y equals x squared horizontally, say 1 unit to the right. To find the equation of the new curve, subtract 1 from x, then square the quantity x minus 1 to reach the original curve. Plotting this at x, we get y equals x minus 1 squared. This equation represents horizontal translation by 1. We can also translate the curve horizontally by any amount. You get the new equation by replacing x by x minus that amount. The graph is translated to the right of the origin if the amount is positive and to the left of the origin if the amount is negative. We can alter the shape of the parabola by a change of scale in the vertical direction. We multiply x squared by a scaling factor. The parabola opens upward if the scaling factor is positive and downward if the scaling factor is negative. Now let's start with the equation y equals x squared and perform all three transformations. Horizontal translation by an amount we'll call h. Vertical scaling by a factor we'll call a. And vertical translation by an amount we'll call k. No matter where we move the graph, y is a quadratic polynomial in x. To see this, square the quantity x minus h multiply by a, add k, and rearrange the terms. The new equation expresses y as a quadratic polynomial in x. This number, which doesn't depend on x, is called the constant term. Changing its value translates the parabola up or down without changing its shape. The number that multiplies x is called the linear coefficient. Changing its value doesn't change the shape of the parabola, but it moves the curve to various positions in the plane. The shape of the parabola is determined by the number that multiplies the highest power of x, called the leading coefficient. If it's positive, the parabola opens upward like this, and there is a lowest point or valley on the graph. If the leading coefficient is negative, the parabola opens downward like this, and there is a highest point or peak on the graph. This point where the parabola has a peak or a valley is called the vertex of the parabola. The Cartesian equation can be expressed in terms of the coordinates of the vertex. Let's use Cartesian equations to find where this line intersects this parabola. Every point on the line satisfies y equals mx, and every point on the parabola satisfies y equals x squared. So, at a point of intersection, we have both y equals mx and y equals x squared. To find the possible values of x, we do a little algebra. And we find two intersection points, one with x equals m, and another at the origin. An arbitrary line may or may not intersect a parabola. If it does, the number of intersection points is either 1 or 2. Points where the horizontal x-axis crosses the graph of a quadratic polynomial are called real zeros of the polynomial. They can be found by solving a quadratic equation. The zeros are easy to find when the polynomial is expressed as a product of linear factors. For example, this product has one zero at x equals 2 and another at x equals minus 1. See what happens as the zeros move further apart or closer together. The lowest point on the parabola is always midway between the two zeros. When the two zeros coincide, the lowest point is on the axis, and we say the quadratic has a double zero. When a quadratic has no real zeros, like this